So this is our first lesson about greedy algorithms. What is the basic idea of greedy algorithms? Imagine that you are trying to climb a mountain, but it's a very foggy day, and so you cannot really see the top of the mountain. Instead, the only thing you can see is perhaps what's happening very close to you. And so myopically you can try to move in the direction that gives you the maximum, the steepest increase in altitude. Of course, if you start moving in that direction, there is no guarantee that you will reach the top of the mountain. The very simple reason is that you may get trapped in some local maximum, and from that point you may not know how to reach the top of the mountain. This is the basic idea of greedy algorithms. They make decisions at every step myopically based on the direction in which they will get the maximum benefit in whatever they're trying to do. However, there are problems in which the greedy algorithms actually give the optimal solution, and we will talk about some of them in this part of the course. Just to explain a bit more how greedy algorithms work, consider the following very well-known problem called the set cover problem. So here you are given a set S of some elements, numbers, characters, whatever, and you are given n subsets. Each of these subsets has elements of the set S. The goal is to compute the minimum number of such subsets such that the union of those subsets will cover all the elements in S. For example, if I have the set S of all the letters from A through K, and I have these 8 subsets of these elements, you can ask yourself, what is the minimum number of such subsets that would cover all of these elements of S? In this case, you can see that the optimal solution is actually S2, S4, and S7. So with S2 you get A, B, C, D, with S4 additionally you get E, F, G, and with S7 you get H, I, J, K. Now if you would try to solve this problem using the greedy approach, you would first try to choose one subset that would cover the most elements of this set. As you can see, that subset would be S1. So with S1 you cover, so in the next iteration you would see that the set S2, for instance, would cover only one additional element. The set S3 would cover only one again. The set S4 would cover 3, the same with S5, and so on and so forth. If you do all of this, you will find out that the set that your greedy algorithm would pick next would be either S4 or S5, because these are the two sets that have the largest number of elements that have not been covered yet. So assuming that you pick either S4 or S5, you would cover also. And now you still have to cover C and J. So given that these two elements do not appear they do not appear together in any set, you would have to pick two more sets. The set S3 would give you C, and the element J you would need to pick either S7 or S8. So to summarize, we have seen here an example where even though the optimal solution would require only 3 subsets, the greedy approach would end up with 4 subsets. Now, how would you know in practice whether a greedy algorithm is optimal or suboptimal? Usually what we do with these algorithms is that we start with some counterexamples. We try to find cases that would clearly show that the algorithm is suboptimal, like the example I showed you earlier for the set cover problem. After a few minutes, if you cannot find a counterexample, then you can start suspecting that perhaps the greedy algorithm is actually optimal. And there are two or three different ways that we usually rely on to show that an algorithm is optimal. The first one is to show that the greedy algorithm actually always does at least as good as the optimal solution, that it never actually stays behind the optimal solution in every single step of the algorithm. This is a very strong requirement, of course, and in many cases algorithms do not satisfy this requirement. But we will see this in the context of a problem called interval scheduling problem. Another approach is to show that any optimal solution actually achieves a certain optimality bound. And then to show that the greedy algorithm actually achieves the same bound. So in that case, the greedy algorithm should be also optimal because it achieves the same, it has the same value, it gives you the same quality of solution that you would get from an optimal solution. We will also see this approach later today in the context of a problem called interval partitioning. The third approach we will see actually on Thursday will be the so-called exchange argument, where you start from the optimal solution and you gradually change it step by step through some exchanges until you get the solution that is produced by the greedy algorithm. The important thing, however, is that as you do these exchanges, as you gradually change the solution, you never really sacrifice its quality. So if you start with an optimal solution, you gradually change it, but it always stays optimal until eventually you show that you have got the same solution that the greedy algorithm would give you. So all of these three things are different mathematical approaches you can use to show that an algorithm is optimal, and we will apply these three approaches later today as well as on Thursday.